2.14 is sort of less of an actual problem and more of a showcase of some of the more sort of weirder properties of quantum mechanics, especially considering that sort of the hint for this problem just literally tells us how to do it. But regardless, let's do this. So we're asked to find the probability of finding a particle outside of the classically allowed region for the ground state of the harmonic oscillator. And our hint is that the classical energy for an oscillator is 1/2 kx squared, or in this case a squared, and that is equal to this counterpart we're using omega, so 1/2 m omega squared a squared. So if you solve for a, then the classically allowed region goes from negative root 2e over m omega squared to positive square root 2e over m omega squared. So the probability of being in sort of the forbidden region is then 1 minus the probability of being in the classical region. So we take p, whoops, that's in blue, hang on. So we take p to be equal to 1 subtracted by this integral from negative square root 2e over m omega squared to positive square root 2e over m omega squared of magnitude psi naught squared dx. There's a few replacements we can make. First off, we know that the ground state energy of a harmonic oscillator is going to equal 1/2 h bar omega. So we can substitute that into our limits, and we also know that psi naught is equal to m omega over pi h bar to the power of 1/4 multiplied by e to the negative m omega over 2h bar times x squared. So we substitute these all in, and our probability is going to equal 1 minus, and then everything squared, so square root m omega over pi h bar. And then our limits, so we have 2e over m omega squared. If e is replaced with 1/2 h bar omega, then we get 2 times 1/2 h bar omega over m omega squared. So the 2 and the 1/2 cancel. One of the omegas cancel. This leaves us with h bar over m omega. We take the integral of this. We get negative square root h bar over m omega. And then positive square root h bar over m omega. And then we have this exponential e to the power of negative m omega over h bar x squared, since we're taking this e and squaring it to cancel out the 2. And then we close this off with a dx, and instantly you should see that this is a Gaussian integral. However, sort of the problem here is that this isn't bounded by negative and positive infinity. Instead, this is bounded by some constant, which instantly means that this isn't necessarily an integral that we can actually do by hand. We can do the base integral and get an ERF function by sort of doing the substitution that we've done so many times before, which is saying that y equals, square root of m omega over h bar multiplied by x. And then doing the whole thing that we've done, sort of the song and dance we've done for so many problems prior to this. But we can't actually solve this integral because at the end, once we get our error function values, the end result is going to be like something like ERF of 1, which we don't know without plugging into a calculator. So at this point, we're just going to do what Griffiths suggests, which is to just plug this into a calculator. And what this is going to give us is the probability of being outside of the classically allowed region is about 0.157, or approximately 15.7%. Now, the reason why this is interesting is because sort of in comparison to classical mechanics, in classical mechanics, what we have is if we have something like a pit with a ball inside of it, what will happen is that the ball, assuming that we don't add any energy to the ball and it's just sitting inside the pit, it will never have a possibility of sort of ever leaving the pit, because the pit has a higher energy of mgh compared to the energy of the ball, which, assuming that this point is y equals 0, the gravitational potential energy of the ball is just 0. So it has a lower energy than the wall surrounding it. So because of that fact, it can never sort of get out of this well. In contrast, the fact that this probability is non-zero in quantum mechanics implies that if we have the same situation where we have like a particle trapped in a cage between two walls, something like this, for example, there's a non-zero chance of the particle just appearing somewhere like here or like here, for example. And that is something that's very sort of fundamentally different from classical mechanics, and it sort of comes from this idea that everything's based on probabilities. And we can get a better look of this also by sort of graphing out the classical region. So if we take a graph of sort of let's call this the magnitude of psi squared versus x. And then let's say that we also want to superimpose a graph of the sort of harmonic oscillator potential energy. So the harmonic oscillator potential is a parabola, and it looks something like this. And then psi naught is a constant multiplied by e to the negative x squared. So that is a Gaussian function. It looks something like this. So instantly, what we see here is that sort of at this point, this is the point where the potential of the well sort of becomes larger than the energy of the particle. And at this point, sort of in classical mechanics, we would expect sort of the potential to instantly just go to zero. Or not the potential, but the wave function to instantly go to zero. But it doesn't go to zero here. So this right here is the actual probability of finding sort of our particle in the classically allowed region. And this over here is the probability of sort of finding our particle in the forbidden region, the classically forbidden region. So in quantum mechanics, apparently, it's sort of possible for our particle to be found outside of the classically expected region. And once again, this is because everything is based on probability. There is no such thing as the determinants in sort of quantum mechanics, with a few exceptions, such as energy. Things like position and momentum all are based on probability distributions. Particles have probabilities of being in certain locations. So evidently, barriers, or at least finite barriers, evidently sort of damp the probability but don't get rid of it entirely. The exception to this, and the one it sort of is the only exception to this, is the case where we have an infinite square well. So that's what we dealt with like 2 sections prior, when we were dealing with a particle with inside of a square well where sort of the walls go up to infinity. And in this case, the wave function actually does have to just cancel out to zero. But this is the only case. This is the only case where sort of the classical system sort of agrees entirely with the quantum system. In any other system, in any realistic system where infinite wells aren't possible, the wave function sort of doesn't go to zero right away. It sort of tapers off exponentially over time. So what that means is that there's always sort of a non-zero probability, although it might be very negligible to the point where it'll never realistically happen in our lifetimes. But there always is a probability of sort of things that we would consider to be impossible in macroscopic classical mechanics to just randomly occur by chance in quantum.